And so today he's going to talk about his research on the isotope record and the precipitation data he has been doing in Thailand. Okay, so let's welcome Professor Ludvig Löwemark.
谢谢. Okay. Maybe we can close the front slides so we have a little bit more contrast. Yeah, that's better. Okay, so yeah, I was asked to talk a little bit about my research, and I think this is the research that is mostly related to the IPCS. And I don't want to give a lecture. I want to more talk about my research and then present why I'm doing this, and then we're coming to the basics of isotope geochemistry, and then I'd like to have more like a discussion. I mean, this is a seminar, not a regular class, right? So I was expecting a little bit more students. So that means the few of you who are here, you will have to answer more questions. But basically, because if I just talk and show you a picture and then we move on to the next one, actually we don't really know if you really understood. And I think the purpose, if I spend 2 hours, you spend 2 hours talking about oxygen isotopes in precipitation, I think we should really make sure everybody has grasped the basic concept, not just heard it once and then go home and do something else. So when I ask a question, do you understand this? How does it work? Basically, we will not move on to the next slide until some student has answered. Even right or wrong. I mean, now it's the pressure that we have a video here, so any stupid answer will go right on YouTube, so maybe you become very famous. Okay, so this project, as I was mentioning before here while we were waiting, this is actually a spin-off project of a spin-off project of another project. So I was in Sweden. I'm from Sweden. I did my undergraduate studies in Stockholm, then I moved to Germany, then I did a postdoc, first in Academia Sinica and then NTU. Then I moved to Sweden. I spent 5 years at Stockholm University as an assistant and associate professor, and then in 2013 I came back. So this is a project that we started when I was in Stockholm. And the project, I will talk more about it, but it was focused on looking at long records of climate change in Thailand, looking at the Holocene, the last 10,000 years. But while we were doing that, we got interested in what is controlling isotopes in the precipitation. And so I will talk more about that. But so why are we interested in precipitation? Well, precipitation is very important. When it rains too much, things break and it's very expensive. This is a picture from a flooding event in November 2011 that hit Thailand. So it was raining a lot in central Thailand, northeastern Thailand, and because it's very flat, and all the villages have tried to build dams and walls to get rid of the water, so all the water was channeled downstream and ended up in Bangkok, and Bangkok is extremely flat. It's basically at sea level. So only the boardwalks and the streets are about sea level. The rest of Bangkok more or less is at sea level. So when all this rainwater came down, and at the same time they had high tide and the winds were pushing water towards the coast. So the rainwater had nowhere to go, and this resulted in a huge flooding. So this is the local domestic airport, and you can see the airplanes were flooded to their bellies. There were, I don't know how many millions of US dollars were lost during this flooding. So obviously it's important for us to understand what is controlling these events, how often can they happen, what is the magnitude, and as you probably know, this is the carbon dioxide curve. So you can see here, this is when Keeling started to record this at Hawaii in the 50s, I think, yeah, 50s. And since then, carbon dioxide has been steadily increasing. So it started at around a little bit about 300 something, and today it's over 400. So carbon dioxide has increased, and what's really interesting is probably more that this is the level where it should be, and this is the level of the last ice age. So you can see the difference here from last ice age to pre-industrial values. This difference is about the same as where it should be and where we are now. So So if the IPCC reports are correct, this will lead, it's already led to an increase of about 1 degree warming globally. And if this continues, we are expecting to see 1.5 to 2 degrees by 2050 or 30 or 50 or something like that. So this is the background. If climate keeps warming, what is the climate going to do? Will these kind of events be more likely? If this happens every 20 years, well, it's an insurance policy, right? If the subway in Taipei breaks down every 50 years, well, not much to worry about. You have to take the bus for a couple of weeks and then they fix it. But if this happens every year, 2 times per year, then society will break down. You will not be able to fix it until it happens again. So it's very important for us to understand what is this increase in carbon dioxide going to do to climate and these kind of hydroclimatic events. Is precipitation going to increase? Where is it going to increase? How much? Some places maybe it will decrease. So this is the rationale for doing this research. So this is a comparison. This is model data showing the modern June to September mean daily precipitation for 1979 to 2003. So this is historical data, and you can see but there are quite big variations. And this is the difference, model difference for the future, 2075 to 2099. So this is the difference in daily precipitation. You can see like maybe 3 millimeters per day doesn't sound so much, but if it's accumulated, if all the rain for that month comes in one day, for example, it can be a big difference. But what's interesting here, I think, is to see that some regions will, according to these climate models, some regions will become drier, other regions will become wetter, some regions will become much wetter, and so these models forecast quite big changes in the hydroclimate. But this is just a computer model, and so how can we know if this is actually true? We don't have time and money to wait until 2075 to see if the climate model was actually correct or not. And that's where paleoclimate comes in. So paleo records of past climate change, they are useful for 2 main reasons. Apart from being academic interest, they're also interesting because you can actually use paleo records to test numeric climate models. So if you reconstruct climate, say in Taiwan, 1,000 years ago, what was the climate 1,000 years ago? And then you run your climate model with conditions for 1,000 years ago, and the climate model gives you the same result as your paleo record. Then you can trust your model. And if you, so that's one reason why paleo records are important, because we can test the numerical models under conditions that are different from today. 1,000 years ago, climate was warmer. We had a medieval warm period, so climate was a little bit warmer. So the boundary conditions are not the same. And if we go even further back in time, say we test like 20,000 years ago, if the climate model still produces good results that are consistent with what you see in the climate record, then you can really trust your climate model. So that's one reason why it's interesting. The other reason why paleo records are important is because they can give us an envelope of what is possible. Because paleo records record extreme events, they record the average conditions. So by looking at paleo records of, say, flooding events, typhoon frequency, and so on, we can say, okay, if in the last 100,000 or 1 million years, we never had more than 20 typhoons per year, well, that's probably the maximum what we can expect. So it gives us an envelope of what is possible under different kind of environmental and climate conditions. So that's why we study paleo records. And as I mentioned, this is a spin-off of a spin-off of a spin-off. The original record, the original project was to look at climate archives from the Korat Plateau. It's a big area here in northeastern Thailand, very flat. So we went there, we took cores in a lake, and the lakes, they of course accumulate. So the sediment at the bottom is the oldest, and then more and more sediment pile up, right? So if you take the core and pull it out, then the deepest sediments are the oldest, and then gradually they become younger and younger and younger. And because in a lake we have a lot of organic material, leaves and grass and stuff that we can use for radiocarbon dating, so we can get a pretty good age model from the lake. And then we look at the composition of the lake, and then we can, because different kinds of sediment correspond to different conditions, and then we can make a reconstruction of what the lake was. So here they reconstructed less runoff, for example, and here higher runoff. But this is, lake records are pretty coarse. They are good for recording long-term records, but they're not very good for recording very rapid swings because the sediment pile up quite slowly. So we can say, we can reconstruct something general about this area, but if you want to know more details, we have to look for other records. And that's when we realized that in the western part of Thailand, there are a lot of limestones. And in limestones, you often have caves, and in caves, you often have stalactites and stalagmites. And the stalagmites are very good climate records. So we started oops. Okay, I put this in in the wrong order, sorry. I was preparing this over the weekend, and then when I opened the file just before this morning, I realized I saved it down the wrong file. So I had to update my old file, and very quickly this morning fix everything. So there's maybe not everything is in perfect order. So this one, for example, should not be there. So caves are very good climate recorders. So if you want to know what the precipitation is doing, we can look at cave records, because the caves, they are fed by precipitation from the clouds. The water, the rain, lands on top of the cave, goes through the cave, comes out in the ceiling, where it forms stalactites, and then the drops will fall from the stalactites, land on the floor, and build up these stalagmites. So stalactites are the ones growing from the ceiling, stalagmites are the ones growing up from the floor. And the good thing with the stalagmites are that they grow like layer by layer. So gradually the calcium carbonate precipitates on top, and the next layer will of course be younger and younger and younger. So at the top, if the stalagmite is still forming, still growing, then that's present day conditions, and then as we go down, back, at lower levels, we go back in time. And so stalagmites are very neat because they're made of calcium carbonate, and on its way through the rock here, the water dissolves calcium carbonate, and it also dissolves uranium. And uranium is radioactive, so when the uranium that is dissolved in this water droplet lands here, it precipitates, is built into the calcium carbonate, and then it starts to decay. You know how radioactive decay works? So you start with uranium, and it's radioactive, and every now and then it will fall apart, emitting radiation and become another isotope. And at the end of this chain is thorium. So uranium will decay through several steps into thorium. So if you know that you start with 100% uranium, and then you can measure how much uranium and how much thorium you have. The more thorium you have relative to uranium, the older it must be, because you start with 0 thorium, 100% uranium, and then this relationship will change. So the more uranium you have, the more thorium relative to uranium, the older it is. And Professor River in my department, he has a lab set up to do this. It's a world-class lab where they date stalagmites and corals and other things. Everything that contains uranium basically can be dated. So this is very important because that can give you absolute age control, because uranium decays with a very, very specific rate. So if you can measure uranium and thorium, you can actually date these layers with a precision that is unbelievable. And it goes back very long back in time. So it's no problem to date stalagmites that have grown over the last 50,000 years or so with very, very high precision. The other nice thing about stalagmite is that as the rain falls here, it dissolves calcium carbonate, and then there's a lot of interactions, and then the calcium carbonate precipitates here, but then the oxygen in the calcium carbonate, to a very large extent, actually comes from the water, from the rain. So the calcium carbonate preserves the oxygen isotope signal of the rain. So the only thing we need to figure out is what does the oxygen isotope in the rain mean? What is controlling the oxygen isotopes in the rain? If we can understand that, we can actually measure it in the stalagmites, and we can reconstruct variations in the climate in the past. Everybody follow it so far? Okay, so that's why caves are so interesting, because they give us this very high resolution, very, very precisely dated record of changes in precipitation. But how do we interpret the oxygen isotopes in the precipitation? And that is why I started my little project, because a lot of the paleo studies, they assume that what is controlling it is the amount effect. So there is you can see here on this plot, this is from a textbook on isotope geochemistry. So you can see on the y-axis we have variations in precipitation, and the other shows variations in delta O18, the oxygen isotope variations. And this is an example from Australia, in the middle of Australia, Alice Springs. But this was actually discovered, the amount effect, that the correlation between the higher, the more precipitation you had in an individual rain event, there's an inverse correlation, so that the lighter the isotopes are. So you can see there's a trend here. So the small rain events have heavier values, and the heavy rain events have lighter isotope values. So if this is universally true, then all you have to do is to measure the delta O18 in the calcite, and you check here your relationship, and then you get the precipitation, how much it was raining that month or that day. And this is in many of the studies that deal with speleothems, they simply assume that this amount effect is universal and is always present, and that you have a correlation between your measured delta O18 values that you can then, via this regression line, get precipitation amounts out. However, when this was first noticed, it was Dansgaard, who is a pioneer in atmosphere isotope chemistry. He noticed that this effect was due to evaporation of low amounts of rainfall. So when it rains, if it rains very heavy, the air is the humidity is very high, so you have very little evaporation from the raindrop. But if it's a small rain event, then the raindrop on its way down, there can be evaporation from the raindrop on the way down, and because the lighter isotopes, O16, in the water will evaporate faster than O18, so the smaller ones will become enriched in the delta O18. Okay, this is...
So that's where the errors come from, right?
Sorry?
That's where the errors come from. You get the data from the raindrop.
Yeah.
Okay.
So if the rain has one isotopic composition and then the raindrop is falling, and you remove the lighter isotopes, then of course the isotope signal, by the time it reaches the ground, it will be much lighter.
Yeah.
No, it will be much heavier because you remove the lighter. So if you have, like, water is looks like Mickey Mouse, like this. It's hydrogen and oxygen. And oxygen comes in two different isotopes. So it's 16 and 18. So this one is actually quite a lot heavier than this one because it has two more neutrons, right? The oxygen here. and this is 16. The atomic weight is 16, and here's 18. So it's actually the molecule. This molecule is actually quite a lot heavier relative to this one. Because these are 1 each, so this has a total mass of 20, and this would have a total mass of 18. So that's a 10% difference. So when they are evaporating, the lighter ones will evaporate easier, and the heavier ones will be left behind in the water. So that's the basic principle. And the idea was then that, okay, so when the raindrops are falling, if it's a dry atmosphere, a light rain event, then you will have a very strong fractionation because they can, if water is in dry air, it will evaporate faster. But if it's a strong rain event, you have very humid air and there will be very little fractionation on the way down. Lots of bigger raindrops and they probably fall faster. Okay,
so the longer the raindrop in the air, the more it will be lighter, right? When you see
the rain that falls should be heavier because
yes.
Okay. Because from the raindrop the lighter isotopes are being removed. So what's remaining when it lands is enriched and heavier. So you can see that the small, so this is the rain event, 140 millimeter is a lot of rain. And here 10 millimeter per whatever is a light rain event, and you can see that these events typically have heavier isotopes because the light isotopes have evaporated away. Okay, so this is the basic assumption that governs almost all studies of caves, that you assume that the amount of water in the precipitation is controlling the delta O18, and that goes straight into the stalagmite. So by measuring the delta O18 in the stalagmite, you get the measure for how much precipitation there was. So if there's a lot of precipitation, you should have heavier values here, and lighter values, and vice versa. So there's inverse correlation. But the original study said that this was true for low amounts of rainfall. So there's this correlation is valid in some instances, but if you have really a lot of precipitation, like we have in Taiwan, for example, or in Thailand, where it rains 2 to 3 meters per year, we don't have many light rain events, and they are totally overprinted by the heavy rain events. So, but most of the paleoclimate studies, they rely on this amount effect, so they can say it would rain more by measuring the oxygen isotopes in the stalagmite. They can say it rained more or less, and then they tie that to El Nino or some other weather phenomenon. But it's like actually several layers away from the original data. And that's why I was interested in doing this study and actually measure the isotopes in the precipitation and try to figure out what is actually controlling the oxygen isotopes in Krabi, which was the region we were studying. So, so this is the base of my study, and now I would like to go into look a little bit at the basics of what is controlling oxygen isotopes in precipitation, because there are actually a large number of different processes that influence oxygen isotopes in precipitation. Okay, students, do you feel you understand what I'm talking about so far? Okay. Because if you have you dealt with oxygen or isotopes at all before? You heard about it?
Yeah, absolutely.
So isotopes in climate science, and especially in paleoclimate, isotopes is, I mean, one of the fundamental processes that we rely on, because different processes will fractionate against or for different kinds of isotopes, against the heavy one or for the light ones, and that gives a different isotope signal, which we can reconstruct, and it tells us something about the environment. Okay, so one of the first things they noticed when they started to measure isotopes in precipitation was that there seemed to be a very strong correlation between mean annual air temperature and the delta weighting. So when we measure oxygen isotopes, we measure it relative to a standard. So this SMOV, that is actually standard mean ocean water. So sometimes somebody pulled up a bucket of water and say this is the standard, and since then all measurements of oxygen isotopes in water are measured relative to this standard. So that means that when you see delta weighting values measured in per mil that are lighter, minus means that your sample is lighter, has more O16 than relative to 18 than the standard mean ocean water. And if the values are heavier, like here, above 0, then that means you have more oxygen 18 than in the mean water. Anyway, so that this shows you variations in delta weighting, and you can see there's a very nice line here from warm climates. The precipitation in what is this, North Atlantic, and then as you go to polar, the Greenland and Antarctica, where we have very cold air temperatures, we have very light climates. So they realized there's a very strong correlation between temperature and precipitation. And actually, water consists of oxygen and 2 hydrogen atoms. And maybe you know that hydrogen comes in 3 different isotopes. It's the hydrogen, which has only 1 proton. And then we have deuterium, which has 1 proton and 1 neutron. And then we have tritium, which is used for nuclear bombs, and it has 1 hydrogen and 2 neutrons. So tritium doesn't really occur naturally on Earth, but it's around now because of the hydrogen bomb tests. Anyway, so of course that means that you can not only measure the difference between oxygen isotopes in water, but you can also measure the relationship between hydrogen and deuterium, the 2 naturally occurring isotopes in water, because the ears of Mickey Mouse here can be either both hydrogen, or 1 can be hydrogen and 1 deuterium, or both can be deuterium. So the deuterium isotopes, they behave in a very similar way to oxygen. So the heavier, if the ears of the water are heavy, then of course the molecule becomes heavier and there is a fractionation. So the lighter isotopes also evaporates easier than the heavy one. So when we look at the plot of the deuterium values versus the oxygen values, you see that they also plot on a nice straight line, where the warm regions have relatively little fractionation. They are close to the standard mean ocean water, 0, 0, and then both oxygen and deuterium values become lighter and lighter and lighter to the cooler air temperatures you go.
So that's the function of the evaporation rate.
Yeah, so
Okay. And it's also a function, because the evaporation is a function of the temperature, right? So it makes the difference.
yeah, so both deuterium and oxygen isotopes are fractionated. So this fractionation is stronger the cooler the air temperature. So when it rains out, if the air temperature when the raindrops fall is cooler, the fractionation will be stronger, and so you have this stronger fractionation in cooler regions. There's also something called the rainout effect. So when the evaporation, ocean water is typically 0 because that's our standard. So and when the evaporation takes place, we form a vapor, but because there's a fractionation, so the heavier water molecules stay behind and the lighter ones are evaporating at the higher rate. So the cloud, the original cloud of water vapor that forms is depleted. It's lighter because it has more light isotopes than heavy isotopes. So then it starts to move, the cloud is moving, and then we have a rainout event. And then, of course, when the rain draws its raindrops from a cloud, which has an average isotope composition of -10, but during the rain event, there is a fractionation. So you can imagine that if we look at these two water molecules, which one is going to rain out first? The heavy one, right? Because it's heavier, so it will want to rain out faster. So when the rain that falls from this cloud rains out, it's actually enriched in the heavy isotopes, which means gives it a heavier signal. So the rain that forms from this cloud is 10% heavier than the vapor source. And that means that the cloud that continues then inland, because we removed heavy isotopes from the cloud, that means the cloud is lighter than it was from the beginning. So next time it starts to form rain, again, the heavy rain isotopes will fall out first, they will precipitate first and form raindrops, and then, but they draw from a vapor source that is lighter, right? So they will, although they are also about 10% heavier than the cloud, they are still not as heavy as this rain. So as this can continue step by step, the cloud becomes lighter and lighter and lighter because we remove the heavy isotopes. So the cloud becomes lighter and lighter, but the rain also becomes lighter and lighter and lighter because it's drawing from this lighter vapor reservoir. So this may be a little bit counterintuitive. You might think, oh yeah, the cloud becomes lighter and lighter, and the rain should become heavier and heavier, but that's not the case. The rain is always heavier than the cloud, but because the cloud, the source of the vapor, or the source of the moisture, is being depleted, so the rain is also depleted. That means that the rain that falls close to the coast, close to the source, will be heavier than it is further inland, and if you go really far inland, the oxygen isotope signal will be much lighter than it was close to the coast. So this is something that is very important to take into account if you are analyzing variations in oxygen isotopes in the precipitation, that it has undergone this sequence of repeated rain events which has depleted the cloud, and we see a gradual decrease in the delta weighting values inland. One student already gave up. Okay, so so when we're looking at longer records, you can imagine that this actually plays some role. If we're looking, so my study region is here, Krabi in Thailand, and today, during the interglacial, the warm period, all of the Sunda shelf here, which is part of the South China Sea, is covered with water. But during the last glacial, when a lot of the water was bound in ice sheets, sea level was lower because you have evaporation, it falls as snow and forms ice sheets, and these ice sheets were really huge. That means that the water level in the oceans dropped by 120 meters. That means that surrounding our study area, there were actually large areas that were land at that time. So you can imagine that water vapor that is coming from here, it will have a lot of time to actually rain out. And that means that the clouds that are passing from here to here will become lighter and lighter and lighter. So when it finally rains here, this rainout effect can have a huge influence. Even if climate, there's no other difference, but the fact that the rainout will cause the isotopes to change into lighter values. So this is a map showing variations in delta weighting for precipitation. It's based on annual data, and you can see that in tropical regions we are close to zero, and then the further north or south we go into cooler regions, the values become lower and lower because of the temperature effect. So there's another example of a correlation between monthly air temperature and the delta weighting. You can see that there's a In most places of the world, there's a nice correlation between air temperature and delta weighting values. So, if there are temperature changes in your region, then you have to take that into account when you're interpreting the delta weighting values. Another effect is elevation or altitude effect. So this is these are three different places where they look at they measure precipitation at different elevations, and you can see there's a very strong correlation. So the higher you go, the more depleted delta weighting values, and that's of course, you know that temperature decreases with about 6 degrees per kilometer. So if you go from here to Jiashan, we would expect to have like almost 20 degrees cooler air temperature than we have here. And if you go up 101, it should be 3 degrees cooler than we have here. Okay, so this is also something that needs to be taken into account. That temperature and elevation influences the delta weighting values. So the fractionation processes that influence the water, we have chemical fractionation. They're most often they can be divided into equilibrium processes and non-equilibrium processes, mostly biological processes. But the rainwater is not really influenced by biological processes, but by physical fractionation. And so when so when we're looking at rainwaters, because the source, the vapor source evaporates from the ocean, and then the delta O18 and the delta deuterium, every rain event that we saw, if we go back here to this, so there's a constant offset between the water vapor and the rain, and the same is true for deuterium. So if you measure the rain here and the rain here and the rain here, you will see that they are becoming lighter and lighter. And the same would be true for the hydrogen isotopes. So actually, if we start with the water vapor, which typically has zero values, and then before precipitation, then gradually, every time it rains out, you will get lighter and lighter and lighter isotopes. But they all, because this relationship in fractionation between oxygen and deuterium in the water vapor as it forms precipitation is more or less constant. So they all end up on this line, which is called the global or a meteoric water line. So if you start with one vapor package and then you rain out and rain out and rain out, the rain will become more and more depleted, but they follow this straight line because the difference in fractionation between oxygen isotopes and the deuterium is constant. So why is this important? Well, it's because if a water precipitation that you measure falls on this line, it indicates that no other water vapor sources have been involved in the process. So if you have, for example, typical water vapors that form in tropical and subtropical regions, they fall on this line. But water vapors that form in a very dry environment, like the Mediterranean Sea, for example, they will have an offset because then during the formation of the water vapor, you have a difference in fractionation where the deuterium fractionates much more. But once it's in a cloud and then starts raining out, then the offset between the two isotopes is constant. So if you have water formed over the tropical Atlantic, for example, it will fall on this line, but water that formed from the Mediterranean would form a line that is offset relative, or sorry, it would be on this side of the global meteoric water line. And that's interesting because if you are measuring groundwater, for example, and all your samples measured fall on this line, you can tell that this is groundwater that originated from the Atlantic, but if they fall on this line, it would tell you they may have originated from somewhere else. So which is what I'm going to actually show on this picture. So maybe this is easier to understand than this picture. So So typically the global meteoric waterline is something like this, and you can, so the delta deuterium, there's an offset by 10, and then the slope is 8 times the slope of the delta of 80. But, so in the Atlantic, the North Atlantic here, west of Europe, has a line that is very close to the global meteoric waterline. You can see here the equation is basically it's exactly the same. But water vapors that form in the western Mediterranean, they have another line. They have an offset. The slope is the same, but they have an offset of -22 because it's very dry conditions here. So there's a stronger fractionation for deuterium relative to oxygen. So vapors that are produced here, they fall on this line, and vapors produced by the Atlantic fall on this line. So when you measure groundwaters in Spain, for example, and they fall on this line, that tells you that the groundwaters here originate from rain that came from the Atlantic and not from the Mediterranean, although you're actually much closer to the Mediterranean.
So it means that the source, the distance of the source is different, right?
No, it means that because during the rainout, the offset is more or less constant, so they follow this line.
Yes.
So the reason you have differences is during the evaporation. Under here you have humid conditions, while here you have very dry conditions. So the original water vapor formed by the Mediterranean.
So it depends on the water status in the atmosphere, right?
It depends on the temperature and atmospheric. Yeah, the water vapor in the atmosphere where it's evaporating.
Okay, yeah. Because the slope is mainly from the ratio of the molecular weight, right?
Yeah.
But the intersect here is mainly depends on the wetness of the atmosphere.
Yes.
Okay.
Yeah, so the more humid the atmosphere is, the closer you will be to the global meteoric waterline. But if you have very dry atmosphere during evaporation, you will have a stronger offset. Okay, so that was the introduction. Now we're coming to my study. So you feel you have an understanding approximately about oxygen isotopes in precipitation? Okay, good. Okay, so back to my study. So we were studying the cave that we have with my colleagues and I have been studying is the Tam Klang cave, which is situated here, and there's an airport here which has a meteorological station, and they have to sample the water every day anyway. So we give them a little bit of extra pocket money, and then they instead of just throwing the water away, they put it in a bottle, sealed it, and then they shipped it to Taiwan, where some colleagues at Academia Sinica have measured the oxygen isotopes in the water. So we have, and we started doing this in 2010, and we have continued ever since. So now we have analyzed this up to 2015. We still have a lot of water bottles still in Thailand that my colleague, for some reason, doesn't want to ship. I don't know why. He probably is busy with other things or he forgot it. Anyway, so if we look at the climate in this region, Southeast Asia, we have several general processes at work here. We have the intertropical convergence zone, which reaches its maximum, northern maximum during summer, up here. And in the winter, of course, this convergence zone moves south, and it passes over this region, and then it reaches its maximum down here. We also have strong influence of the monsoon system. So generally, during the summer months, we have a southwest monsoon with winds blowing in this direction, and during the winter, we have northeast monsoon with winds blowing in this direction. But this is an extremely generalized picture, right? Doesn't mean that you can, if you let go of a balloon here, it's going to fly like this. That's not the case. This is just very general. But there's another process that also influences the precipitation here, and that's tropical cyclones, typhoons basically. They form over the South China Sea and maybe also from the Pacific, and then they follow a path at the end of the fall in October and November. There are typically comes typhoons across the South China Sea that deliver a lot of precipitation to this part of Thailand. So it's important to remember that we have several different processes that are influencing the amount of precipitation. And this is just a general picture. Okay, so if we look at the general climate of Krabi from the meteorological office, we see that we have a very distinct distribution of precipitation. So this is monthly precipitation, these bars, how much precipitation you have in a month. So the maximum is October, which is just when ITCC, the intertropical convergence zone, is passing over this area, and it's also the month when we have landfall of typhoons. So both these processes at the end of the southwest monsoon. So all these processes converge to bring a lot of precipitation in October. So during October we have more than 300, and the weakest month typically is January and February, where we have less than 50 millimeters.
So the temperature during the summer is much lower than the spring?
Actually, the temperature, there's very little variations, right? It's, the daily average varies from 26.5 to 28, so the range is very small. But the warmest month, in generally in Thailand, the warmest months are not peak summer, but actually in the spring. So that's when you have the highest temperatures. So the highest temperature here is in what is this, April. And then we see cool, slightly, not really cooler, but less warm temperatures in the winter. Okay, so this is the general climatic patterns. We have a northeast monsoon, and then we have a transition period. So during the northeast monsoon, we generally have quite little precipitation, but because of the landfall of the typhoons, at the end of the fall, October and November, we actually have quite a lot of precipitation anyway. And then during the southwest monsoon, which is the summer monsoon, a lot of precipitation, presumably mostly from, or to a large extent, from the Indian Ocean, is being delivered to Krabi. So this is the general picture, and so now we're coming to my data. So if we just look at the upper panel first, so this is the time axis. From 2010, we started measuring in the summer of 2010, and then we measured until the end of 2015. And we measured every time it rained, they went out, took the collected water, put it in a bottle, and sent it to us. So it's a daily record of variations in precipitation. And of course, they measured how much precipitation you have, and you can see that the peak daily precipitation is like about 140 millimeter in a day. That's quite a lot. Not as bad as in Taipei during Typhoon Nari, though, when we had 1 meter in 24 hours. And we also measured, for each rain event, we measured the oxygen isotopes. And you can see that there's a pretty big variability. And you can see that many of the rain events are characterized by low delta weighting values. And that would indicate that there is maybe some kind of amount effect. And that's why we decided to analyze this a little bit more in detail, because when you look at the monthly averages, so here's the monthly precipitation, the gray bars, and the black curve is the monthly amount weighted average of delta weighting. And you can see that, so even if here there is a suggestion that strong rain events are characterized by decreases in delta weighting, when you compare the monthly averages is not really a clear trend. But we'll see, you can, and also on this picture you can see the turquoise bars are seasonal averages, and the dotted line here is the average of the whole measuring period. So typically we have values around -5 as average. And at the bottom I made calculated the monthly average. So this is the January average in precipitation and January delta weighting value and so on. And so if you look here, you see that although there is a distinct seasonal variability in delta weighting, and there's a distinct seasonality in precipitation, they don't match up. So there's not there's no convenient linear relationship within which would allow you to, from delta weighting, to calculate precipitation, because the highest delta weighting the heaviest delta weighting values are actually not corresponding to the months with the highest precipitation, and the lowest are also not corresponding to the month with the lowest
So
precipitation.
is that because of the source of the water is different?
That's what I don't really know. That's what we're trying to figure out.
Circulation in different seasons will be different, so
Yeah.
they have different source of the water.
We think it's on a monthly basis. It's probably more related to variations in the source region.
Yeah.
And as I was showing in the first slides, it seems that looking at the daily variability is not related to the amount that is raining out, but to local convection. So when you have stronger convection, you have stronger fractionation also. Okay, so we measured, of course, we looked at the meteoric waterline to try to understand if there are any differences in the sources, and as you can see, so the gray dotted line is the global meteoric waterline, and the dots here are our measured data. So we separated them from the winter period and the summer period, and most of them plot nicely on the global meteoric waterline, suggesting that we have no influence of water sources that are coming from any strange places or very dry regions, which would be very surprising since we have South China Sea, very humid conditions, and on the other side we have the Indian Ocean. We also have a fair number of outliers with very heavy delta deuterium values, which we really cannot explain. There's something problematic with these values, but we don't know why. These ones could be related maybe to evaporation after sampling, because these are very small samples, so any evaporation would have a strong influence on the. But these ones we don't really know. But the vast majority falls right on the global meteoric waterline, suggesting that the values are pretty good. So the first thing we looked for was, of course, the amount effect. So this is variations in precipitation versus variations in delta weighting, and as you can see, there's a very there should be minus here, but there's a very weak correlation. And I mean, with just visual inspection, it looks like somebody took a shotgun. There's not really any strong correlation here. So the amount effect, at least for daily precipitation values versus delta weighting, is not doesn't contribute much to explaining these variations. So that also is evident if we look at individual rain events. So here I compare two different periods from March to May 2011, and here August to November in 2011. And during spring, for these rain events, you can see that during these rain events, these strong rain events, there's actually a very distinct decrease in the delta weighting, right? From this background level of around -5, during this rain event, there's a very distinct decrease in the delta weighting, which would suggest that there is a strong amount effect. But if you look at this time period, although we have several rain events that are of similar magnitude, like these ones, there is very little variability. So at least the amount effect cannot be used as a general explanation. So we also looked at the amount effect for monthly precipitation. So this is monthly precipitation versus amount-weighted delta weighting variations, the black dots. And for the monthly precipitation, there's actually a better correlation between, you see here is a R of 0.5 approximately. So but when we look at the seasonal precipitation, there's basically no amount effect visible. I also looked at the monthly averages in precipitation versus amount-weighted values, and there's also very, very weak correlation. So it's a little bit puzzling that when we look at monthly precipitation, we do see a correlation, and that's been seen in other studies too from Southeast Asia, but nobody has a really good explanation, because if it was related to the original amount effect, then we would expect to see that in the individual rainy months, and not when we pool it into the monthly precipitation data. But when we look at, when we compare our daily delta weighting variability against other parameters spatially, we see that when we compare delta weighting versus outgoing long-wave radiation, which is a proxy for local convection, the more local convection you have, that influences the outgoing long-wave radiation. So we see that there is a very, so this is our study reading, we see that there is a very strong correlation between delta weighting and outgoing long-wave radiation, suggesting sorry, that there is a strong correlation in the delta weighting values and the strength of the local convection in influencing the precipitation. We also compared delta weighting to the GPCP rainfall data, and didn't really produce any good correlation. We correlate the rain, daily rain, measured daily rain with outgoing long-wave radiation. There is some correlation, but negative correlation, and we also compared our daily rain with the GPCP rainfall data, and of course then you have a very good correlation. It's not so surprising. But the interesting thing, I think, is that there's a pretty strong correlation between outgoing long-wave radiation, that means local convection, and variations in delta weighting. And similar results were also produced for some islands of India in another study by the India group, where they also saw that the main factor influencing delta weighting in daily precipitation was actually variations in local convection.
Okay, so quick question: why is there a need for local convection to look at the outgoing long-wave radiation here? It's not clear to me.
Okay, so the outgoing long-wave radiation,
Yeah.
so is measured.
On the satellite, right?
Yeah, and when you have a lot of clouds, that sort of catches blocks the long-wave radiation. So
Okay, I see.
that's the
So
rationale.
that's kind
So
of
the
indicator.
more cloud formation you have, the less outgoing long-wave radiation.
Okay, because the temperature is much lower.
Yeah.
Okay. So
That's how-
when the cloud is higher, the bigger. So
Yeah,
the
the thicker.
temperature, the thicker, the
Yeah.
temperature will lower. Okay.
That's how my colleague explained it to me. So.
All right.
Okay, so we also looked, of course, at vapor sources. So this is the delta weighting of ocean water, and as you can see, that it's very similar. The sources in the South, in the Indian Ocean and the South China Sea are very similar. They're all around zero, actually. This is just the actual stations. This map is compiled from these actual stations. We look at the global distribution of precipitation. We see that the average is actually also just slightly above zero, so around -5, which is very close to my average, right? So my long-term average was around -5, which agrees pretty perfectly with this GNIP data. So just show this to show that there is nothing strange with my data series. Okay, one popular way of interpreting variations in delta weighting is to look at the high split, which is a computer simulation to simulate. You can either, if you start at one position and you sort of release a tracer, you can see where it is going, or you can choose your location and then see where the precipitation that is falling on top of you is coming from. So this is the path where the precipitation is coming from during May. So you can see that most of the precipitation in May, according to this simulation, was coming from the Indian Ocean, and just a small amount was coming from the South China Sea. And so this is not exactly my this is from Wei et al. They published a study from Phuket, which is about, I think, 100 kilometers to the west of my location. So it shouldn't be too much difference. And then if we look at September, you can see that most of the precipitation is also coming from the Indian Ocean, right? However, when we look at so this is a computer model, and when you look at satellite images, how the clouds are actually moving in this this region, you see that there's a lot of movement back and forth, back and forth, back and forth. So I'm not so sure I really trust this computer.
That's a very simple.
Yeah, it's a very simple model, and
yes, as a one-dimensional one, it's very simple. So, but you can use that as a reference.
it's a reference to show where the major source region of your precipitation for different seasons. Okay, so oops. Okay, yeah, as I mentioned for those who were here early, I was preparing this presentation on the weekend and then I took the wrong file. So this morning I had to very quickly put together. So some of the slides are not exactly in the sequence I'm expecting them. Okay, so if we look at, so this, what I presented so far is our short-term variations, but if we look at a little bit longer, on climatic timescales, processes that influence precipitation over peninsular Thailand are related to variations in the Indian Ocean dipole, the El Niño, Southern Oscillation System, movement of the intertropical convergence zone. We also have influence of the variations in the Indonesian through flow, where water from the South China Sea and the Pacific are going through the archipelago and feeding into the Indian Ocean. We have variations in the Australian monsoon that have some influence here. Of course, we have the Indian and the Southeast Asian monsoon systems, which have a very strong influence on precipitation in this region. And those systems, in their turn, are actually influenced by variations in the Siberian high-pressure system, and even far-away processes such as Arctic sea ice and the position of westerlies have influence on precipitation in this region of the world. So it's not so easy to determine which of all these processes is playing the major role. But in order to try to assess this, we did a wavelet analysis of precipitation and delta weighting. So you can see this is the time series, and these are the different periodicities. So one is 1 year, and higher values are multi-year cyclicities, frequencies, and these are lower frequencies. And so this is the powers go from red, strong power, and bluish colors are weak periodicities. So what you can see here is that we have typically weak powers on short periods and also on longer periods, but around 1 we have quite strong. And that's, of course, we have a seasonal cycle, a yearly seasonal cycle, right, in precipitation. So that shows up very clearly in precipitation. And when we look at variations in delta weighting, we see a similar pattern with the strongest periodicities at 1 on the yearly seasonal variations in precipitation, which is show up in delta weighting. What's quite interesting is that 2010-11 was a La Nina year, so we have here you can see that it's a weaker power in the periodicity, and during El Nino we have stronger. It's not so clear in the delta weighting, but there is a weak tendency. However, my time series is only 5 years, and the typical period of El Nino is like 4 to 6 years or so. So probably this time series is simply too short to say anything about the relationship with La Nina and El Nino. But this is what we have to work with. So another factor potentially influencing this on a little bit longer time scale is the Indian Ocean dipole. So during a positive dipole mode, we have warmer waters on the African side and cooler waters here, and we have more precipitation here where we have white patches. And during a negative dipole mode, we have cooler waters here and warmer water here in Indonesian archipelago, and more precipitation here. So we would expect that if there is obviously the Indian Ocean dipole influences precipitation over my region, but the question is does that show up in the delta weighting values? We also have influence of the El Nino, normal conditions. We have rain here over the western part of the Pacific. During El Nino, this shifts, so you have most of the rain falling the warm water shifts to South America, and you have much more precipitation here in the winter months. And La Nina is an extreme case where the warm water is shifting towards the western part, and you have much more precipitation over Southeast Asia. So to address this, we compared our data with indexes for El Nino and Indian Ocean Dipole, and so these are variations in delta 18, monthly precipitation, and monthly amount average delta 18 values, and the monthly precipitation. And we couldn't really find any clear-cut correlation between variations in El Nino and Indian Ocean Dipole, but that's probably a gain because we are looking at a relatively short time period. So what we are seeing in these indices are actually just seasonal changes, and we don't see the long-term change in the El Nino or the Indian Ocean Dipole values. Another possible influence is the Martin-Julian oscillation, which is a atmospheric phenomenon where you have upward motion and heavy precipitation, stormy and wet conditions, and in the downward motion part of the cell we have sunny and dry conditions. And this atmospheric cell is moving from the west towards the east, and it takes about 1 to 2 months for this whole cell to pass over a certain area. So it has a periodicity of about 1 to 2 months. So if this plays an important role in controlling the delta weighting values, then we would expect to see a correlation between our variations in delta weighting. So this is a comparison over 1 year from July 2011 to July 2012 at our site, variations in daily delta weighting values, and this is a Hove-Muller diagram showing how this Martin-Julian phenomenon is moving from, so here's the east, and here is, the west, and here's the east, and this is the time, so you can see how this pattern is moving from the west towards the east. And our site is situated somewhere here, so if there was a strong correlation between delta weighting values and the Martin-Julian oscillation, we would expect to see a cyclical variation corresponding to the values here, but my colleague who is a meteorologist, modeler, he couldn't find any correlation here. So the conclusion is that the short-term control on delta weighting in the precipitation is to a quite small extent controlled by the amount effect, but that the local convection actually plays a stronger role. So now I'm almost finished, and it's almost 2 o'clock. So we understand. We think that we know that on short-term variations in delta weighting is primarily controlled by these. But how are the delta weighting values going into decay? And the factors that are influencing the drip water, apart from the atmospheric processes, you have the rainout, you have temperature, we have amount effect, we have variations in source of evaporation, and so on. But we also have many processes influencing the delta weighting values after the rain has landed on top of the cave and recharged the atmosphere. So you can have evapotranspiration, evaporation of the precipitation as it lands on top of the trees. Water is being sucked up by the roots and evaporates from the stomata of the leaves. You also have soil processes that can influence the delta weighting values. Sometimes you can even have exchange processes with a host rock, and maybe most important is that you may have mixing in the reservoir. So we don't really know, because a karst reservoir is very heterogeneous. You may have open spaces, you have diffuse transport of water inside the aquifer before it then comes out, and then in the cave. And then of course variations in temperature in the cave may also influence the delta weighting value as the new calcium carbonate is forming. So when we looked at, skip this one. We actually have two short time periods of drip water from the cave. So in 2013, we took one series a little bit more than a month from August till September, and then we took the second time series in end of October to the end of the year. And the idea was to sort of cover summer monsoon and versus winter monsoon conditions. And as you can see, the delta weighting values are very similar to the yearly average, around -5. And we see some variability, but basically the signals are very muted. And if we look at the delta, the global meteoric waterline, we see that almost all the values fall right on the global meteoric waterline, suggesting that there's no influence of any local sources. If there was, for example, standing water body that would evaporate and then sort of produce local precipitation, you might expect to see some offset here, but actually there's very little influence of any local water sources. So this suggests that everything is actually coming straight from the ocean, either South China Sea or the Indian Ocean. But when we compare our time series with the precipitation for that time, you see that the average, so these are monthly averages, the blue bars and the black dots are daily measurements. You see that the average is very similar to the average in the cave. And we do see that there are some of these big events, like for example, this shift towards heavier values could correspond to this one, and this decrease to lighter values could correspond to this, and this decrease here maybe corresponds to this one, but that is highly speculative. But if so, then there will be some mechanism that with a lag of a couple of weeks, some of these extreme events would be passed through the cave system, the aquifer, and then come out as cave drip water. But basically the lesson learned is that the cave drip water has a signal which is very close to yearly average, and that's probably what is being preserved in the calcium carbonate in the stalagmites. So probably what the stalagmites are giving us is yearly average precipitation. Okay, so final slide. So my conclusion from this little study is that there's relatively weak support for the amount effect, but there is some correlation which we cannot really explain yet in the monthly data. There is a strong correlation between delta 18 and outgoing longwave radiation, suggesting that there's a strong link to local convection, controlling the short-term variation of delta 18, and cave drip water is very close to yearly average, although there's some indication that perturbations or extreme events can be seen with a couple of weeks delay. Don't need to take pictures, the whole lecture is on the Okay.
All right.
Thank you. Any questions?
Thank you. Any questions from the here?
I have a sort of technical question. When you show that the precipitation delta overlaid with the delta OAT, sometimes there's maybe during the heavy rain event, there's a variation in delta OAT or something. How that occurs?
You mean this one?
No. I think in the earlier slide.
This one?
Yeah. For example, in 2011, there seemed to be multiple delta OAT value at the heavy rain event.
Yeah. So, and then that's what you would expect from if there was a strong amount effect, then you would expect to see something like this. But there isn't. I mean, when you look at the time series, there's the correlation is very, very weak. So it seems that some events, there is a correlation, like when we looked at the individual rain events here. So where you have strong precipitation, you have an inverse correlation with lighter delta 18 values. But it's not a general So,
Yeah,
and if the amount effect should have any explanatory power, then it must be valid for all rain events, right? If it's just, you can't just cherry pick the ones that show this effect and then assume that if it's, because it doesn't show up every rain event. So I cannot really explain why some of these, especially this event, it seems to have a very strong effect. But you have a lot of other events where you actually don't see any amount effect.
So I have a question from here. So the precipitation amount you show here is for one single event, or that's
single day events.
Single day event.
Yeah.
I have a question here because if, for example, if you have 100 millimeter for one day, but the duration of the rainfall is different. For example, one is for 1 hour, another is for 10 hours. The intensity is very, very different.
Yes.
So the raindrop, the size of the raindrop is different. So I expect to see the difference in your isotope measurement, right? But here it just shows us 1 day.
Yeah.
So that could be the error of the virus, right?
That could be one possible explanation, because if it rains for, if this event, which is almost 150,
Yes.
if it keeps raining the whole day, it divide 150 millimeters on 24 hours. But here, if it comes maybe all of it in half an hour,
Okay.
it's a very different kind of event.
Okay, so I was wondering if you go to the next one, right? That's the comparison here.
This one?
So, no, the previous one. Here, so if you change the precipitation data to intensity, do you expect to see the difference here?
We don't have that data. We only
Or
have
just on 1 day?
Yeah,
Okay.
they collect every day when they measure, they give us the
Okay,
data.
because
So
based on your assumption in earlier slides, it depends on the size of the raindrop. So for example, for the rainfall with very big intensity, we expect to see a heavier rainfall, right? And a heavier isotope in your case. So if you cannot separate these two different type of precipitation, it's not easy to see to expect to understand the amount effect.
Yeah.
Okay.
you basically would have to do what Löwemark did in the 60s. He
Yes.
just went out and measured like, I don't know, every 10 minutes or something he collected.
Something like that, yeah.
But that's technically not feasible
Yeah.
to do. I mean, this is already a pretty big amount of data that it's taken a long time to compile. But that is one interesting aspect that we have discussed. That so and that's why I think this correlation to outgoing longwave radiation, that is stronger than the relationship,
Yes.
because this is directly related to the strength of the convection.
Yes.
So I guess if you have very strong convection, you would have like more event-like
If you
rainfall.
have a very strong convection, the cloud height can reach like
Yeah.
8 to 10 kilometers. So you will see a very strong convection in that event. So that's why you can have a data correlation
Yeah.
in this case. Interesting.
So, but that actually makes, I mean, the common assumption that there is a correlation between precipitation and the delta weighting values that you can use from stalagmite records. If you have to go down to like hourly data to see any correlation, then this assumption totally breaks down, because that's not what you can see in a cave record. So,
So, any more questions from the students? Raise your hand. Okay, so it's already 2 o'clock. So let's thank Ludvig again for his wonderful presentation.
thank you for coming. I hope you learned a little bit about
I don't know.
how both paleo records